Welcome, everyone. Let's get started. Today we have Stefan Geier. She's a recently appointed staff astronomer in Grand Decan. This talk today is the first of a series of presentations we're going to get from different staff members in Grand Decan in the next coming months. So we get to know what they're doing, not just their activities, but also the scientific production. Stefan, he carried out his undergraduate studies in Munich, in Ludwig Maximilians University, and then he moved to Copenhagen at the Dark Cosmology Center, where he conducted a thesis with the title very much like the title of the presentation today. And towards the end of his PhD, he moved to La Palma to work in the Nordic Optical Telescope, and then now in Grand Decan. So today is all about cosmic evolutions. Stefan.
Yeah, thank you, Jesus, for that nice introduction. Morning, ladies and gentlemen. I hope you're sitting comfortably, because now I'm going to take you on a journey out very far away into the early universe. So now, first of all, let me give you a quick overview about what I'm going to talk about the next 45 minutes. So first, let me briefly introduce the various galaxy populations at high redshift, and then I'm will continue to introduce some of the general methods which we are using for studying those. Especially I'm going to emphasize how we make use of the gravitational lensing effect to facilitate studies of high-redshift galaxies. I'm going to present a study of gravitationally lensed quiescent redshift 2 galaxies, a pretty challenging topic during the last few years. Then the second part of my talk is going to be about a slightly different topic. I'm going to talk about quasars and Damped Lyman-alpha Absorbers, where I'm going to present the probably most spectacular example of this kind of phenomenon. And finally, I'm going to introduce you to our survey for red quasars, which is closely connected to the research on DLAs. And I'm going to finish with a very quick overview of the research we are currently doing on BAL quasars and the redshift evolution. So let me start with something very simple. So when we look out into the universe, what do we see? So that's basically what we see. We see galaxies. So basically one of the very fundamental questions in astronomy is, how did the galaxies which we see today in today's local universe come to evolve, and how did they come to be during the history of the universe? So it's basically a very simple sketch here, so to say, the timeline of the universe. So basically we are talking about the early phases here, a few giga-years after the 2 to 3 giga-years after the Big Bang, redshifts between 2 and 3. That's basically where we are having a look at the early stages of galaxies. And now one of the questions is, of course, how do we find galaxies in the universe? How do we identify those? Now, this here is basically a quick overview about the different methods by which we can select galaxies at high redshift. So basically, most of those are star-forming galaxies, except the distant red galaxies. So probably very well known are kind of selection techniques like the Lyman break technique, and also selecting galaxies by the Lyman-alpha emission. Slightly different population of the so-called sub-millimeter galaxies, which are also star-forming galaxies, but which contain a lot of dust and which kind of reprocesses the light from the stars and resubmit it in a sub-millimeter wavelength. Now, my research fields are more focused on what you see on top of the slide. So, since about 15 years, one has been able to select galaxies as a host of gamma ray bursts, which is also a very hot topic, and which, of course, is also selecting star-forming galaxies. But already at those early times in the history of the universe, there was already a population of passive galaxies, which as a consequence of this are already evolved and display red colors, by which they can be relatively easily selected with color cuts in the near infrared. And finally, also a very hot topic in recent years, also called Damped Lyman-alpha Absorbers, which I'm going to introduce in the second part of my talk. So basically what I'm going to talk about is going to focus around these two populations of galaxies. Now let me briefly, given that this is quite a mixed audience, give an overview of the kind of methods we use. Of course, we can select pretty large samples of galaxies in deep imaging surveys, for example, the Clash survey with HSD. Of course, we are also using spectroscopy from big ground-based telescopes to conduct more detailed studies of individual galaxies, with one of the most important methods of course being fitting stellar population synthesis models to their SEDs. And finally, a very important tool for us is to make use of the gravitational lensing effect of intermediate redshift galaxy clusters in order to enhance the apparent brightnesses of intrinsically very faint objects. So this is a quick overview of what we can do with imaging surveys. So it's basically an efficient way to probe large volumes, and especially for quasars, we can also make use of surveys like the SDSS and UKIDSS. Still relatively cheap in terms of demand on observing time, and in recent years many quite efficient color selections have been developed to select different kinds of populations of high-redshift galaxies. And imaging, especially with HSD, is also very useful in order to investigate the morphologies of those galaxies by fitting, normally by fitting certain profiles. While with spectroscopy we can conduct more detailed studies of individual objects, which is of course more expensive in observing time and thus also challenging. So what we can look at is basically the continuum shape and the spectral lines, and with the help of those we can determine more precise redshift, star formation rates, metallicities, stellar populations, ages, or in case we can detect absorption lines with high enough signal to noise, we can even infer something about the dynamics. Now, probably some of you know the technique of SED fitting. So basically one takes all kinds of data, what you have normally photometric data, but can also include spectroscopy, which is then compared to a library of synthetic models of galaxy spectra. Of course, this technique bears lots of caveats, one of those being that we need to assume a certain IMF, the stellar initial mass function, which is one of the quantities which are not very well constrained, especially at high redshift. And then, of course, furthermore, we input range of star formation histories, metallicities, extinction laws, and the outputs we normally get their ages. More precisely said, what we can infer directly from a spectrum are their luminosity-weighted ages, stellar masses, star formation rates, and optionally, if we cannot infer redshifts from spectral lines, we can also use SED fitting to infer photometric redshifts. As already mentioned, the whole thing is not trivial. There are several degeneracies, for example, between age and metallicity, and also age and extinction. And also there can be multiple solutions and also catastrophic misfits. So with this in mind, let me present you my first paper, which conducted on spectroscopy of two gravitationally lensed quiescent galaxies at redshift 2. So let me briefly introduce this actually very intriguing population of galaxies. So basically, this is a population of galaxies at redshift around 2, between 2 and 3, which means that an epoch about 2 to 3 gigayears after the Big Bang. But already at these early times, these galaxies turn out to be already very massive and already very evolved. So they already shut down the star formation, pretty old stellar populations. And for that reason, they also exhibit very red colors. Very important characteristic feature in spectra of passive galaxies is the so-called Balmer 4000 angstrom break, which occurs in galaxies above an age of a few hundred megayears. Now, some of the very striking properties of this kind of galaxies is first extreme compactness. So basically, we are looking at galaxies which have roughly the same stellar mass as the Milky Way has, but condensed in an effective radius of about 1 kiloparsec. And one of the potential explanations is that this is due to the higher densities in the early universe. In terms of morphologies, it's not quite clear, because there seems to be like 50-50. Half of them seems to be more disk-like, with static indices around 1, and the other half seems to be more spheroid-like, with static indices around 4. Which is in general difficult to measure, because, just as a rough estimate, 1 arc second at the redshift 2 corresponds to about 8 kiloparsecs. So basically, we can only resolve those galaxies using deep HSD images. And of course, one important caveat could be that we might be missing out on some low surface brightness. So basically, that those galaxies only appear that compact because we might miss out on some faint low surface brightness components. So when we look at redshift around 2, the Balmer 4000 angstrom break is redshifted into the near infrared, basically somewhere in between the J and K band. For that reason, those galaxies exhibit very red J-K colors, and with a very simple color cut of J-K above 2.3, we can very effectively select those galaxies. The population has been named so-called distant red galaxies, or short DRGs. And in fact, this population of galaxies comes into flavors, as we used to call them. There are not only those truly quiescent galaxies which are red because of their old ages, but also dusty star-forming galaxies which are also selected by this color cut. So especially in the case of quiescent galaxies, we only have continuum and absorption lines in their spectra. And furthermore, as the bulk of their stellar light is redshifted into near-infrared, it means that spectroscopic studies of this kind of galaxies are very challenging, because as you all know, the sky background at near-infrared wavelengths is much higher than its optical wavelengths, so this makes observational studies of these galaxies pretty difficult, especially in terms of observing time. So fortunately, we can make use of basically what we call the biggest telescopes in the whole universe. So basically, we're using the strong lensing effect of intermediate redshift galaxy clusters, which means that redshift around 0.5 roughly. So the advantages of this approach are that, first of all, gravitational lensing is boosting the apparent luminosity by orders of magnitude. And another very interesting advantage is also that lensing conserves the surface brightness. So thanks to the enhanced angular resolution, it's also easier to study their morphologies. And the most important advantage actually is that with this approach we can, within reasonable amounts of observing time, study galaxies with more typical luminosities, meaning luminosities close to a star. which basically are roughly 1 million times more frequent than the galaxies with the highest luminosities, around 15 L-star, which had been studied so far, and which were basically the limit which was feasible without the use of gravitational lensing. Yeah, quick illustration with one of the most spectacular lensing clusters, in the case of BAL2218. Now, these are a few cutout images of the two gravitationally lensed galaxies which I studied in my paper. So these have been selected in the fields of the galaxy clusters Abell1413 and MACS2129. And especially in the case of MACS2129-1, we see that basically at first glance this looks like basically as if it was a disk galaxy at a lower redshift. But since this was selected by the DRG color cut, it was clear that this must be something at higher redshift, and indeed it turns out that this is galaxy around redshift 2, which has been stretched to an arc by the lensing effect. Now, what we did, we obtained a few hours of spectroscopy with the extruder spectrograph from the VLT for those. And so basically, based on previous studies of more luminous, more massive, unlensed galaxies, we expected this to work with exposure times around 3 to 5 hours. But unfortunately, it turned out that the spectra of those two galaxies did not show any detectable absorption lines, no emission lines, of course, and but also no detectable absorption lines. So what I ended up doing in the end was spinning the data to extract some signal to noise and basically do some SED fitting on the bin spectra. And furthermore, we had deep HSD images available to study their morphologies. So that's the near infrared spectrum of one of those galaxies. So basically what we see is lots of noise, some continuum, but no clear absorption lines. So what I basically did was taking those spin data points, which you see in green here, and fit scalar population models to those. And as a further parameter, also determine their redshift. So basically, it's as if this were photometric redshift. So this here is a quick overview of the results of the study. So these two galaxies turned out to be at redshift of around 1.7 and 2.15. And in fact, with those quasi-photometric redshifts in mind, we were able to tentatively detect some absorption lines with a significance of about 3 sigma, which then also confirmed those redshifts. And then with the results of the SED fitting, we also knew the reason why it was impossible to reliably detect any absorption lines. And the reason was simply the very high ages of those galaxies. So they turned out to have ages around 2 gigayears, and which are much older than the seed galaxies which had been studied so far, for which stellar ages of only a few hundred megayears had been found. And since especially the Balmer lines become weaker with higher ages, this was basically the explanation why we couldn't detect any absorption lines. We also did not detect any H-alpha emissions, so with that we could place pretty tight constraints on star formation, on potentially ongoing star formation, which means we could also confirm that these are truly quiescent galaxies, and which were magnified by about 0.6 and 1.5 magnitudes, as we could infer with the help of those infrared redshifts. So we also reconstructed their morphologies by fitting static models to them. So MACS2129, that was the one which we see turned out to be indeed a kind of a disk-like galaxy, which basically means it could be kind of a high-redshift analog of S0 galaxies, which we see at basically in the local universe. And this is basically the first spectroscopically confirmed galaxy of that type around redshift 2. The other galaxy turned out to be more spheroid-like, with a physics index around 3.3. And we also could confirm that also those two galaxies are very compact, as we can see in this comparison. So what we see here, the red and blue lines, that's basically the relations for local galaxies from the SDSS sample. And everything below this black line is basically defined as being very compact, with the two galaxies in our study being around here. So basically the conclusion is that this was the first detailed study of gravitationally lensed quiescent galaxies around redshift 2. And so for the first time we've come a bit closer to the typical luminosity of galaxies, basically closer to L star. But still, with only two galaxies, one cannot, of course, not make any big statistical claims. So more work needs to be done. So we're going to select bigger samples from imaging surveys which we have available of strong lensing clusters. So we have the HST flash survey available, and also lots of ground-based J and K imaging. And of course, this will be a very interesting topic also for instrumentation, which is coming up at our telescope at Canarias. For example, with the EMIR instrument, we will be able to conduct multi-object spectroscopy in the infrared, which will be basically perfect for the study of this kind of gravitationally lensed galaxies at high redshift, because we can basically will be able to combine different science cases, not only studies of quiescent galaxies, but also other types of high redshift galaxies, which are lensed by these intermediate redshift galaxy clusters. And with that we'll be able to reach a much higher efficiency, covering many galaxies in one cluster field. And also the studies in the near infrared will basically be kind of complementary to the short survey, which was carried out with the medium band filters at Canarias, but which covered the optical wavelength range. Now this was basically the first part of my talk. Now let me move on with a slightly different topic. I'm going to present a study on the galaxy counterparts of two high-metallicity Damped Lyman-alpha Absorbers toward QSO at around redshift 3. So now, what is a Damped Lyman-alpha Absorber? So here we have a rough sketch of this kind of phenomenon. So basically, DLAs are more a kind of phenomenon and less a kind of object. So what we have is a quasar at a high redshift, and in the line of sight towards the Earth, there is some galaxy at a lower redshift, and basically using the quasar as a background light, so basically as a cosmic torch, so to say, which can shine through the outskirts of those galaxies, which may have huge reservoirs of molecular hydrogen, which we basically cannot see in emission, but which, thanks to the quasars, we can see in absorption. So basically what we see is the spectrum of a quasar, and superimposed on the spectrum of the quasars is the Lyman-alpha absorption of the intervening galaxies. So here we're seeing this from a different perspective. So basically with the DLAs, we are able to probe the outskirts of of the galaxies and their halos, whereas with, for example, with gamma ray bursts, we're rather probing the inner region of galaxies where the bulk of star formation is ongoing. Now, when we see this kind of phenomenon in the quasar spectrum, we know there must be an intervening galaxies, and indeed, during the last roughly 30 years, more than 10,000 of these objects have been discovered. However, it has turned out to be very difficult to identify the galaxy counterparts of the system. So up to now we know more than 10,000 DLA systems, but the galaxy counterparts were only detected in a bit more than a dozen cases. So for many years there have been many failures while searching for the galaxy counterparts of DLAs. And actually it turned out that the few detected systems all turned out to be relatively metal-rich. So this was already a clue that this might have to do with the mass-metallicity and thus the luminosity-metallicity relations, which in the meanwhile also have been confirmed for those redshifts. So, furthermore, what has been confirmed in recent years is that chemical evolution makes kind of a turnaround at this redshift, around redshift of 2.5. So basically above redshift 2.5 there is no evolution in the mass-metallicity relation, whereas at redshift 2.5 we see a very sharp onset of the evolution in the mass-metallicity relation. Now let me present you the most spectacular example of DLAs which we found so far. So these have been discovered towards QSO at the redshift of 3.07. So at first only a DLA at the redshift of 2.58 was known, and when we took some deep X-shooter spectra of this system, the other DLA was basically discovered serendipitously. So we have this very lucky case here that we have two intervening galaxies in the line of sight towards that QSO. And interestingly, it turned out that those DLAs seem to be very metal-rich, which meant that there should be a very high chance to identify the galaxy's counterparts for those. So here we see HSD images of that quasar. So this is the bright background quasar, and here at a distance of about 2 arcseconds, which corresponds to roughly 16 kiloparsec, we see one galaxy, and but unfortunately we cannot say here, there was another galaxy around here. So what we did, we obtained some deep X-shooter spectroscopy to investigate whether those galaxies could be the galaxy counterparts of the two DLAs. So the first galaxy turned out to be at a redshift of around 1, so it could not be responsible for the DLAs. But indeed, this galaxy here, at a protected distance of about 16 kiloparsec to the QSO, turned out to be the galaxy counterpart of the DLA at redshift 2.58. And that's quite an intriguing result, because we have, so this is basically the DLA with the highest known impact parameter, and so this is very remarkable. So we are looking at a redshift of 2.5. We're looking at an impact parameter of about 16 kiloparsec, which is about more than 10 times the size of the optical emission of the galaxy, which turned out to have a half-life radius of about 1.3 kiloparsec. So this means this galaxy must have a huge diffuse halo of molecular hydrogen with a very high metallicity, which is already a very intriguing result. And indeed, after subtracting the continuum of the quasar, we were detecting the O3 emission of that galaxy in the spectrum. And furthermore, we also detected the galaxy in ground-based imaging, which we obtained with SNOT. And with that, and combined with the near-infrared photometry from HSD, we we're able to construct a rough SED and infer some basic properties like the ages and star formation rates of this galaxy. And indeed, it turns out to be a relatively massive galaxy with a stellar mass of around 10 to the 10 solar masses, which basically confirms the picture that those high-metallicity DLAs stem from rather massive and luminous galaxies. We were also finally able to detect the other DLA galaxy in emission. So after continuum subtraction, we detected the three lines at a very low impact parameter, so basically at the same position of the quasar itself. And actually, after PSF subtracting the quasar, we think we see kind of a hint of the host galaxy. It's not very significant, but basically this must be at a very low impact parameter. So, as I already mentioned, this basically confirms the picture that high metallicity DLAs have the brighter galaxy counterparts, which makes them easier to find with the instrumentation we have available now, and with more sensitive instrumentation, and also in the era of the ELTs, we will finally be able to also identify galaxy counterparts of more metal pure and faint galaxies. Now this redshift 2.58 system turns out to be very remarkable, with an effective radius of 1.3 kiloparsecs, but an impact parameter of 16 kiloparsecs, basically more than 10 times as much. But still, what we find there is a large column density of gas and pretty high metallicity, basically with a solar value. So one of the explanations might be that this may be an outflow rather than pristine gas, which might be inflowing. Now, furthermore, in the system we see evidence for dust extinction. So when fitting this with LMC and SMC-like curves, we infer that this must be a rather dusty sightline, which points us to the issue that in traditional quasar surveys, we must be missing out on this kind of system, because traditionally quasars like the STSS selection, for example, are selected based on optical colors, which concentrate on rather blue objects, and which must be missing out on red objects like this particular quasar, for example. So, motivated by this particular discovery, we have developed a new kind of color selection for those red quasars, where we make use of the combined photometry from the SPSS in the optical, as well as the UKIDSS survey in the near infrared. So the first sample, which we published about 3 years ago, contained about 50 of those quasars. But it turned out that the efficiency was still relatively low, and furthermore we were missing out on the quasars in the redshift range around 2.5 to 3, which would be a very interesting redshift range where we expect to find also lots of those DLA systems. So what we did, we refined this color selection, conducted a new survey, which we conducted with the AlphaScale instrument at the NOT, and we during about 3 years we collected about 150 spectra of those red QSOs, and indeed what we were finding was a variety of unusual QSOs. We were finding QSOs with very steep extinction curves. We were also finding several QSOs with intervening absorbers, also 1 or 2 DLAs. And we were finding QSOs with excess emission in the infrared, and also some with a deficit in the terrestrial infrared emission, which we could explain by emission from hot dust, or vice versa, the lack of hot dust in case of deficiency of infrared emission. Yes, this is one example of QSO which is likely being reddened by foreground galaxies. And furthermore, we are also discovering relatively distant QSOs out to redshift beyond 4. This is an example of a borderline absorption quasar, BAL quasar at redshift of 4.25. And actually it turns out that we find a relatively high fraction of these objects in our survey, and which, as a very interesting byproduct of our research, enabled us to directly infer the fraction of BAL quasars at those redshifts, and we were even able to infer the redshift evolution of this type of quasars. So basically, with other surveys, the problem was that there's a very heavy selection effect, and so it's very much biased against those red quasars, and due to the broad absorptions, also BAL quasars exhibit very red colors. So up to now, people had to make complicated calculations to correct for those selection effects in order to infer the intrinsic fraction of BAL quasars. But thanks to our survey, we were now for the first time able to determine this BAL fraction more directly. So this is the first, also quite tentative result, but what we see here is a clear dependence of the BAL fraction on redshift. And now when we recall what we know, is that basically lots of interesting things seem to happen in the history of the universe at redshift around 2.5. You remember my previous slide where we found that there is an onset in the evolution of the Mass-metallicity relation around the redshift of 2.5. Furthermore, we know that quasar activity and the number count of quasars in the history of the universe also peaked at the redshift of around 2.5. Furthermore, we know that the global star formation rate peaks around the same redshift. And now, when we determine the redshift evolution of the BAL quasar fraction, we also found a very sharp peak at exactly the same redshift. So looks like we might be finding kind of the smoking gun for the connection between quasar activity and star formation. So, but of course, as we see with the limited statistics we have, so basically we had a survey of about 150 quasars in which we identified between 40 and 50 BAL quasars. So due to the still relatively poor number statistics, the error bars are still relatively high, and this result is only significant at the 3 sigma level at most. So basically, I've now given you a very rough overview of some of the research fields which I'm involved in. So basically, I've reached the end of your talk. Thank you very much for your attention. And questions, please.
Questions? Well, it is more a comment than a question. You mentioned this, that a lot of things happen around redshift 2.5 or something, the half of the edge of the universe, let's say. And many other things happen as well. For instance, you stop the star formation, you stop the construction of clusters, and many other things. I remember a paper, it was in a magazine indeed, it was in the Scientific American by Concelis, many years, I don't know how many years ago. But he pointed this probable solution. It is that the expansion of the universe was dominated by gravity. I mean, it was a decelerating expansion until that age, more or less. And from that, the dark energy gain, I mean, it was the accelerated expansion was more predominant. So that happens also in that region of the edge of the universe. So maybe what we are looking at is a transition from domination of gravity, in which you have more mergers, you have more construction of, I don't know, the quasars themselves. And then when you have the expansion, the accelerated expansion, you lose all that opportunities of having the galaxies close together. I haven't seen any other paper on that, because that was in a very strange channel, because it was an outreach magazine. But have you heard about this, or what is your opinion on
it? Relatively seems to be an interesting idea. I mean, that's rather a cosmological approach, whereas what we do is more from a point of view of galaxy evolution. So what we are trying to figure out, and what we intend to do with further observations during the next years, is to figure out this connection between quasar activity and star formation. So basically, those BAL quasars could provide us with a clue of the interplay. So basically, the truth is that this BAL phenomenon is still not very well understood. There are several scenarios, and it looks that this year may give us the opportunity to finally figure out the true origin of BAL quasars, and to establish whether there is indeed a connection between quasar activity and star formation. I mean, it's something which seems to have suspected for a long time, but it looks that we might have found this the smoking gun for that.
Why do you take for granted that all DLAs are associated with galaxies, rather than being intergalactic gas?
It's a good point which you're making here. I mean, you saw our example that we're finding a galaxy with an apparently very huge reservoir of gas. I mean, it could be, of course, but this is probably very related to an issue which we had while we were preparing the study, when we were looking at this galaxy at this very high impact parameter and wondering how it comes that we are finding such a high metallicity so far away from the galaxy. And a very obvious thought, and basically every time we present this, we ask this, whether we could rule out that there might be another galaxy. So basically there could be this galaxy at redshift 2.58, and with another associated galaxy at the same redshift, but at a small impact parameter closer to the QSO. But the thing is that we actually do not detect any emission at that redshift close to the quasar. And thanks to the Mass-metallicity relation, we know that this must be a relatively bright galaxy. If it was a very faint dwarf galaxy, we would not be able to detect it, but we can relatively safely rule out that it is such a small faint galaxy because of the Mass-metallicity relation.
Yeah. Can I? It's about the metallicity of the DLAs. Is it easy to understand how do you measure the metallicity of the DLAs? How do you know the metallicity?
Well, what we found was a variety of absorption lines. Fortunately, I submitted a slide where we made a detailed analysis of several metal lines. So yes, this seems to be a relatively robust result.
But you have to assume temperatures, densities to derive from the fluxes that you measure the abundances. So is it strongly model dependent? No, I'm talking about the metallicity of the gas. So the DLAs, the metallicity of the DLAs, or you're talking about the metallicity of the stars in the galaxy?
Well, basically we are talking about the metallicity which we measured in the gas, 16 kiloparsec away.
Yeah, but so how do you determine that metallicity?
Well, basically from the absorption lines.
Yeah, but does it require deep modeling, like assuming densities and temperatures, or?
Ooh. Well, actually, that was not exactly my part of the study. Need to have a closer look at the paper again. I mean,
okay.
Yeah.
I will.
Can I give you that many details right now?
Following on this, to what extent the failure of detecting the counterparts of DLAs is due to the fact that you need to subtract a huge QSO, the lead of the QSO?
Yeah, of course. That's of course.
Is that something something that is a big concern. Is that the main? Is that the main reason, or not? Do you think you guys can model the BSF?
Also that, and also note that, for example, for this we also did not find any Lyman-alpha in emission. So basically, DLA galaxies seem to be more drawn from the same sample as Lyman-break galaxies, rather than Lyman-alpha emitters.
Any more questions? Last one.
So it's because you have been talking about so interesting, intriguing things that the BAL quasars, they are very. I mean, I'm not working on that field, but I know that those are quasars that have very strong absorptions to the red of Lyman-alpha. That if you think that is produced in the quasar itself, it requires motions of the orbital speed of light. So, do you have? I mean, what is the model or the idea that people have to understand?
Not sure exactly about this quantity, but it's basically what we're seeing is what the general paradigm is. So our suspicion is that we're looking at huge amounts of dust being driven by the central engine, by the AGN. And basically now, as we're improving the statistics on those, and with this sample, we might begin to understand the dependence also on the opening angles and the different models where we've furthermore found some dependence on luminosity and also secondary effect, there's a dependence on the AV values. So this, but as I mentioned, this is basically an ongoing study. So this is the stuff which I've shown at the end is from a paper which is currently under review and which we are actually heavily debating with the referee about this result. So this is kind of a preliminary result, and I have to emphasize again that this is an ongoing study where we're basically trying to figure out the nature of BAL quasars.
Okay, good. So I think it's time to go for coffee, but let's thank Stefan.